The next talk is by Professor Arcavi from Transient University. He will talk about early kilonova observation.
Okay, thanks for sticking around. I will make it quick. So I want to take you back to the kilonova. We've heard a lot yesterday and today about it, but I think almost all of the open issues we've heard about, the opacity, the composition of the material, the nucleosynthesis yield, the kind of jet or cocoon that was created, the merger product, all of these open issues I think are tied to the early emission, the early optical and ultraviolet emission. And this was not obvious, I think, from the beginning that there would be this connection to the early emission. So I want to first show you the observatory that we use to follow up the neutron star merger and how it helps us obtain this very early data. So our observatory is unique. Instead of one telescope at one site, our observatory is made up of 21 telescopes at 6 different sites. 3 different classes of telescopes, but all the telescopes of the same class are identical. So we don't really, we can get observations from anywhere and put it all together very easily. So this allows us to respond very quickly. No matter what time of day the alert comes in, no matter what hemisphere, we should be able to have a telescope that can observe it. The other unique thing about our observatory is that it is completely robotic. So there is no one operating these telescopes. It is fully robotic and is scheduled fully robotically. This is just an example of the schedule of all the 21 telescopes a couple days ago. So the way it works is if you want to use this telescope, you don't have to worry where you need to observe everything. You just tell the scheduling software, I have this part of the sky I want observed in these time constraints. And it takes thousands of these requests from everyone and solves this like 21-dimensional Tetris game and puts everything in, and then it redoes it every 15 minutes as weather changes and condition changes and requests change. So you can actually get an observation within a couple minutes from when you click the button to request it. So this kind of dynamical nature is very useful. So in the whole scheme of things for this kilonova discovery, we were one of the groups that obtained the earliest observations, the earliest optical emission from this. So how did we do that? So initially, actually, this looked like quite a hopeless cause for us because this is what we were told would be a typical LIGO localization. And that, to scale, is the field of view of our cameras on the sky. Okay, so this looks like a hopeless task. And here again, we have to thank Geralds for telling us that this is actually not a hopeless task, that we can do it, and we've heard about this yesterday. The strategy, of course, is you don't really have to tile the entire region. You have to look at where the mass is, and the mass is, of course, in galaxies. And so there's still a lot of galaxies to look at in a typical region like this. But it turns out that most of the mass is concentrated in a small number of galaxies. So this was what was in Neil's paper. That even when the range is 100 megaparsec and your localization is 100 square degrees, 50% of the mass is located in about 20 or 30 galaxies. And this is a very manageable number. So if neutron star mergers follow mass, then we have a 50% chance of finding it by just observing 20 to 30 galaxies. So this was our strategy. The other advantage of looking at only the massive galaxies is that we know where they are. So galaxy catalogs are pretty much complete out to a few hundred megaparsec for the massive galaxies. This is completeness for the top 50% of the galaxies. We don't know where all the small ones are, so if neutron star mergers were to prefer small galaxies, this would not work. But it seems like they don't, they just follow the mass, and so we are able to find them this way. So combining this all together, we have this fully automated system. When LIGO sends an alert, we listen for it, we grab the localization, we have an algorithm to prioritize which galaxies to observe first, depending on where they are in the localization region. And we can send that automatically to our telescopes, and they can start observing, and all of that can happen within a few seconds. We don't need any intervention on our part at all. And this worked quite well on August 17th, where here is the Fermi and LIGO localization. Here are the galaxies that our algorithm came up with. This is the full moon for scale. So again, we would never, even this 30 square degree region, we would not be able to tile. But we were able to observe the galaxies, and NGC 4993 was a galaxy ranked number 5 by our algorithm, 5th most likely to have the kilonova, and there it was when we took that image. Okay, so another important thing about this specific event that I think was not mentioned until now is that that part of the sky was visible for a very short amount of time. Actually, this thing, if it were to happen 2 weeks later, we could not observe it from the ground. So this is a time since the merger, and this is the altitude. So, okay, if you're an observer, look at the left axis, air mass. If you're not an observer, look at the right axis, altitude above the horizon. So that part of the sky, when the night started, was setting very quickly. And after an hour, you could not observe it anymore. So here is when the merger happened, the localization arrived 5 hours later because of this glitch that Ray mentioned yesterday. And this will turn out to be very important for this story. But then the first site where this was visible after the localization was Chile. And you had this 1 hour and a half about window to find the kilonova. And then if you have a regular observatory that's in Chile, you have to wait 23 hours until you can observe it again. So for the rest of the night, it's below the horizon. Okay, but our observatory is different. So here's what you could have gotten if you only could take one data point, one observation every night. So you would have gotten this very rapidly evolving, declining light curve. Okay, but as I mentioned, our observatory is in 3 sites in the southern hemisphere, so we can observe it 3 times a night. Chile, Australia, and South Africa, and then this turns this data set into this. Okay, and this reveals a lot more details of what is happening, especially for something so rapid. Specifically, you'll notice that we now see that there is some even kind of rising phase in the light curve between the first 2 observations in Chile and Australia, which you totally miss if you don't have this multi-site capability. So another thing that worked well for us is that this was quite bright and blue at early times. And there was a lot of talk about this blue and red kilonova, but I don't think anyone has showed this plot yet, which I like from Brian Metzger's review, which is kind of I don't want to say random walk, but walk that theorists have made in their models of kilonovae predictions. So it started, with the early models predicting it would be quite bright, but then people realized that the heating process is our process heating, so turned out it would actually be a little bit fainter, and then, there might be lanthanides with large opacity, so actually it would be fainter and longer and redder, but there actually might be an ejecta with low lanthanide fraction, so maybe it'll be bluer and brighter. And then there might be this additional component at very early times, which I will talk about later. So, the models were kind of not sure what we should expect. So here is our data compared to a model with very low lanthanide fraction that you need to reproduce this very bright optical emission, and still it doesn't reproduce the bluest emission. This is G band, the bluest band. It still underpredicts that. And this problem is worse when you combine our data with everyone else. So here I want to show you, this is my compiled light curve of all the published ultraviolet, optical, and infrared data on the kilonova. I think this is one of the best observed transients in history, at least per unit time. And so here you can see in kind of faded circles the original data. So you get some idea of the scatter between the different groups and the different observatories and instruments. And I just combine them. But of course, if you want to do something more accurate than that level of uncertainty, we need to reprocess everyone's data in the same way. But for now, you can get this idea of what the combined light curve looks like. So ultraviolet is down here, optical is here, infrared is up here. And I should say this compilation appears in a paper that was accepted on Saturday. Okay, so you feel free to use this plot. And the model I showed you before, this single component model that was kind of engineered to fit the optical data, you see that it under-reproduces the UV emission at early times, and it under-reproduces the infrared emission at late times. So this is the same thing Elena was saying yesterday, that you cannot fit the data with one component. Because if you want to fix the UV discrepancy, you need to decrease the opacity. And if you want to fix the infrared discrepancy, you need to increase the opacity. You can't do both things at once. So you cannot fit it with one opacity, one velocity, one ejecta mass. Okay, so what are the different solutions people have come up with? So one is, take multiple components. So this is the fit from the Villar et al. Paper, where they take the classical radioactive heating model and just put 3 separate independent components, 3 different opacities, 3 different masses, 3 different velocities. So the low opacity material is used to fit the blue curve, the early time, and the high opacity material is used to fit the red curve, and there's an intermediate opacity material to make it look better in the middle. And this fits quite well, and there is actually also physical motivation to do multiple components. We've heard yesterday and today the numerical models show that there is multiple ways that mass can be ejected from a neutron star merger, and these multiple components will have different properties. So the tidal tails are expected to be high opacity, lanthanide-rich material that will be contributing to the red emission. We heard about this polar ejecta that comes out from the merger contact region that is shock heated and will maybe have a higher electron fraction and will contribute to the blue emission. And then, depending on the merger product, you could have an accretion disk and winds, and they could be lanthanide-rich or poor depending on what this merger product is. Even if it's a very short-lived neutron star, we heard about this neutrino irradiation that can cause it to be high electron fraction and contribute to the blue emission. So there is some motivation. And the interesting thing is, if we can really identify which part of the light curve is coming from which part of the emission, we can constrain a lot of physics, because the tidal tail mass, for example, the amount of material in the tidal tail is sensitive to the mass ratio. If you combine that with the gravitational wave chirp mass, you can get better constraint on the individual masses. If you believe the blue emission is coming from the polar ejecta, that is sensitive to the radii of the neutron stars. So now you can get a mass radius constraint. Actually, people who have done that, they get that if the blue emission is coming from there, the radii are about 11 kilometers. They're quite small. And then, if you think it's coming from the disk winds, then you get some constraint on how, if there was some high mass neutron star and how long it needed to live to make that emission. Okay, so it would be very useful if we could really do that. But there are alternative models. So that was the multi-component radioactive decay that I told you. There has been also a model saying it's only one mass component, but the opacity evolves over time, and the velocity that you see changes over time. So that would be a different picture than what I showed you. And then we heard about this boosted ejecta yesterday and today. If you have some amount of material at very high velocities, the relativistic boosting will cause it to be blue, and that will explain the blue material, the blue emission. And Zvi talked about this shock cooling, this double peak light curve. There is actually a model that says that the entire blue emission at the beginning, that is the first peak. That is the shock cooling peak. It's heated by thermal shocks rather than radioactive heating. And then the second peak is the infrared thing we see later. So this has also implications, if there is high moving, high velocity relativistic ejecta, if that's what's causing the blue light curve, that is evidence for this cocoon model. So is the shock cooling. This is where it would be generated. And but if it is, the polar ejecta, that helps constrain the viewing angle. So here's the H0 cosmology constraints with the viewing angle axis. So that is where the uncertainty in the viewing angle that we heard about comes in. And so if we can constrain the viewing angle from the optical or blue emission, that will help constrain also the distance measurement and the Hubble constant. So here is the model for the cocoon. So this explains the red emission by using high opacity material and the blue emission by using this high velocity boosted emission, and it fits quite well. But I want you to notice there's one qualitative, there's one quantity here that is, or quality of the light curve that does not fit very well, and that is this very early rise that I showed you before. So you notice that the first epoch looks like it's on the rise, and these models are continuously declining. So I should say this is a very unfair comparison that I'm making, because these models were designed to fit a subset of the data that was available to those modelers at the time, and now I'm comparing it to the full data that we have later. So it's actually curious to see if this model can be adjusted to actually fit that rise. And that was the one we noticed first with our observations between Chile and Australia a few hours after the merger. And actually, I think in the circulars were doubted. People doubted that this rise was real. But I'm happy that now when we combine our data with other people's data, you see this rise also in other filters. So the R-band data collected in Chile and the R-band data collected in Australia by other groups also shows this rise. You see at least a flattening in the G-band. And you see it, of course, also in the infrared. So I think this rise is real and is an important property that needs to be reproduced by the models. So here's that early light curve again. Same data on both panels. The first 3 days of the optic UV to infrared emission with 4 different models. So the solid lines are the radioactive, purely classical radioactive decay models. You see they do a better job of rising on a 1-day timescale, and that's because of the diffusion time is about 1 day in these models. So they reproduce this behavior a little bit better. And then the dashed line over here is the boosted emission, which is declining from the beginning, and the shock cooling emission, which is also declining. So it's kind of hard to say in terms of which one fits better, right? So it's hard to say, because if you look, for example, in the R band or G band or V band, one model under-predicts it and one model over-predicts it. And they're kind of the same distance away from the data from the two different sides. So I think it's hard to say which model is correct and which model is wrong based on this data. But I think we're very close to be able to saying that, because you see that the models are different the earlier you go in time, the more the models diverge. So really the early time would have told us, a few hours earlier, which one of these is correct. And I just want to point out that this glitch that caused the localization to be delayed by 5 hours, had we had the localization at even just 1 hour before, the same exact algorithm that ran in our telescopes in Chile would have run in our telescopes in South Africa, and we would have found, we would have observed NGC 4993 5 hours earlier, and we would have had a data point 5 hours earlier. And that one data point would have solved this whole problem, because it would have told us if it, how fast it was rising or if it were declining. So this is why very important for us to get the localization as soon as possible. The other point you will notice is that the difference is larger in the ultraviolet bands. So the difference between the models is, even for the discovery epoch, 10 hours later after merger, if we would have had an ultraviolet point, that would have also helped discriminate, right? And so most of the difference is what was the ultraviolet doing at this time. You see that the first ultraviolet epoch is delayed from the first optical epoch by a few hours. And that is enough to incorporate all this ambiguity. Okay, so you can say, well, okay, I don't care what the individual bands were doing. I don't trust the models that well. What is the overall bolometric luminosity doing? Just is the overall luminosity rising or declining? That's a more robust test of the models. So it turns out that it is actually a little bit complicated to calculate the bolometric luminosity because of this time difference. We don't know what the ultraviolet was doing here. And that ambiguity is enough to change the total luminosity by a large amount. So here is, so you can decide how do you want to calculate the total luminosity on the epoch of discovery. You can take all of the optical infrared points and fit a black body to them without the ultraviolet. Or you can decide I'm going to lump the ultraviolet and the optical points from the first epoch together. So here's what you get if you do either of those things. If you just take the optical data from 10 hours after the merger, it's these black points. You fit a black body, you get about 10,000 degrees. This is similar to what Elena was showing us yesterday in the spectra. If you include the UV points from a few hours later and you say, I don't care about this time difference, I'm putting it all together, that reduces the temperature by about 1,500 degrees. And of course, we don't know what the correct answer is because we don't know what the UV was doing between that and that epoch. But that 1,500 is enough to change the bolometric light curve to fit the model. So here is the bolometric light curve from the combined data set from all the published data together. So just reconstructing the bolometric light curve from all the individual band data. Here's the temperature evolution, radius evolution. You see that after 1 day, 1 to 10 days, all the models pretty much fit the data pretty well. It even fits this heating rate we heard about this morning, T to the minus 1.3, which, without any more sophisticated additions to it, fits quite well. But all the difference is in this first day. So here's a zoom in of that first day. And here are the two options for what the total luminosity was at discovery, if you include the ultraviolet from a few hours later or if you don't include it. And that difference is exactly the difference between was the total luminosity flat or rising on that day, or was it declining already at that first day. And the declining fits these shock cooling and boosted models, and if it was flat, that fits the pure radioactive classical heating models. So really, we were just at the limit where we could tell the difference, and we can't. The models are just right there where we cannot distinguish them. So really, it is all in what was happening earlier and what was the ultraviolet doing just 6 hours before the first measurement. So I just want to mention, we would really like for the next event to get earlier data and just solve this problem with one more earlier epoch. And there is actually another thing we can test if we can go even earlier. So this prediction by Brian Metzger that some part of the ejecta, a leading part, will be moving very, very fast, and there the free neutrons will just decay into protons and produce about an hour, a few hour timescale blue flare. This is if it's at 200 megaparsecs, it's quite faint. But if it's closer or if it turns out to be brighter and we can get on it in the first hour, we maybe actually can measure this and get some additional physical constraints on this process. So there is a lot of advantages to getting on it early. So I want to mention these resources if you want to look at the data yourself. So all of the published data from all of the papers is on this website, kilonova.space. It includes a few of the models that people have fit as well. It's a very useful way to get the data. And also, if you're drowning in the sea of papers that came out on October 16th, a few of us made a list of all the papers that came out on day one. Okay, papers that came out on day 2 and onwards, I am not responsible for. But everything that came out on the release date, you can find at this website, kilonovi.org. So note this is the plural kilonovi. If you just go to one kilonova, you get one group's papers. If you go to kilonovi, you get everyone's papers. This is how to remember it. And then you can sort and search by what you're interested in, the GRB, the theory, the host galaxy, the optical, with specific team, specific publication, whatever. You can find it all there. And if you find anything missing, please let me know. Okay, so I promised I'll be brief. And I will just conclude with my main message that this problem of the early blue emission, I think, is very important. There are different models that were proposed for that. Either it's classical radioactive decay from some low opacity ejecta, which we would learn a lot from, or it's radioactive decay from boosted high velocity ejecta, which would learn a lot but different from, or shock cooling or some kind of combination of these things. And each of these models, if you choose, has implications for a lot of physics. I think basically most of the open questions about this kilonova are tied to the source of this early blue emission. And in order to, for us to be able to say which of these models is correct, we need the very early data. So I totally agree with Zvi, who said earlier today that 10 hours was too late. It was just about too late, though. So if we have a few hours earlier, we will be able to distinguish. And this is why I think this glitch happened this time. Hopefully next time it won't happen. And we will be able to observe it earlier. So I'm optimistic that this is possible. I think our observing strategy shows that we can do it as long as we get the localization early enough. And of course, it would be nice if all the events are at 40 megaparsec and in the 30 square degree region. Okay, so it is very important to get on it early, and it is equally important to be able to observe it multiple times a day, because these are the important time scales where things are evolving at the beginning. Thank you. Well, we can let people refresh before dinner as well.
Okay. First off, just a comment as well. I think I appreciate that people say 10 hours is too late. I think also this time around, the fact that something was sent out was also fortunate. Because, because of the glitch, only one detector really picked it up.
Yeah.
And so had we, for example, not done single trigger search, searches.
I didn't mean to. We were super happy with the work LIGO did, and it was amazing, and it will be even better next time.
I'm just saying that these things are, from our case, the fact that there was, despite this big glitch, that people literally just got up in the middle of the night and take a look, and did all of this. But I agree with you. We will be faster if there's no big glitch there. I actually had a question as well. In one of your earlier slides, you mentioned that you had that this galaxy was number 4 or 5 on the list of things. Yeah. Can you talk a little bit about how you make these decisions, how you rank them, and whether this event or the lessons learned from this event will basically influence future strategy?
Yeah, so our strategy was very simple. Different groups have different strategies. Ours was basically, we rank the galaxies based on their position in the localization region. So the localization region, of course, is probability map. So if it's in a higher probability region, it gets a higher score. Also the distance, we use the distance information that comes in the localization region. So we have the distance to the galaxy. And the third thing we use is the brightness of the galaxy, just as some kind of very simple proxy for its mass. So we prefer the more massive galaxies first. And this ended up to being a more massive galaxy, so it worked out well. Then there is some other tuning that we do for our telescopes, like specifically for our telescopes, where would we be more likely to see it. So if it's close to the distance where we think is our detection limit for a kilonova, we would slightly prefer the closer ones, even if they're in a lower probability region, just because we have some better chance of seeing it. So there is some element that is tuned to our specific capabilities. But that's pretty much it. So we just, the main assumption is that where LIGO says it's more probable and where there is more mass, we will start with that. So we don't yet know if that's a typical, if this was a typical case and if that'll work well next time or not. I think this galaxy was on the top of almost everyone's list, just because it was so massive and in such a good part in the Iair region. We could definitely, we have considered more sophisticated things, star formation history of the galaxy, morphology of the galaxy, but right now it doesn't look like neutron star mergers really prefer a certain type of galaxy population. And also we don't have that information for all of the galaxies in the catalog. So for this one, it's an NGC galaxy, we knew a lot, but if the Iair region happened somewhere else and it's some anonymous galaxy, we will only have the distance and the brightness. So that's what we can count on having every time.
I have a question about what you call models and what is used by these different groups. I mean, as far as I have followed this without claiming to know all the details, all of these groups have used parameterized things. None has used models with multidimensional radiation transport. It was also always a combination of components which were dealt spherically.
Yeah.
Don't you feel uneasy fitting your things with high precision with some simplistic?
Yes. So this is why I kept the comparison qualitative. Actually, I intentionally did not want to do any measurements of goodness of fit or anything like that, because the models are not supposed to be that accurate. But just roughly, does a model, what is the rise timescale of the model? What is the light curve shape? Does that match the data more or less?
But can that really be discriminative between the models if you miss all the multidimensionality of the phenomenon?
Yeah, okay, that's a good question. I took the models that were available and asked the question, can the early data distinguish between them? But yeah, maybe we can't trust the models and we need better models.
That's my opinion.
Okay.
So I don't know if this is an appropriate question to ask for this talk, but what is the shortest time you expect, a trigger from LIGO, for example? So obviously, if it's not 10 hours, and what's the earliest?
Yeah, no, I think that's a great question. It depends, I guess, how lucky we are. So as soon as I send a trigger, even if we're sleeping or at a conference or, not paying attention, our telescopes will start observing within seconds. So within seconds of receiving the trigger, if there's a localization attached to it, our galaxy prioritizer will run, will send the observations to the telescope, it will trigger another run of the whole scheduling algorithm, so we have a very high priority program on the network. In fact, we have a mode where it will take off whatever a telescope is observing, not even read it out, just throw it away and observe our galaxies for us. So we can be, from trigger to shutter open on our telescopes can be a few minutes. And then it just depends on what is the real galaxy. If it's number 1 on our list, we got it sooner. If it's number 30 on our list, it'll take a little longer.
Yeah, I'm just wondering if there's a fundamental limit to how short that can get, and if it's dependent on, say, the number of vetoes that they implement in their data analysis pipelines. I mean, because if I was thinking that maybe, okay, so if it takes, 4 hours to get the shortest possible trigger, then maybe they reduce the number of vetoes, give you an earlier trigger, and then maybe rely on optical or some other wavelength to essentially provide some confirmatory basis for their analysis.
That's a great point. So from our perspective, as soon as we get the localization, the fundamental limit is a few minutes. But between the merger and the localization and reporting the localization, that's of course a LIGO issue. And we keep telling them we don't mind to get a lot of garbage if it's quick. So, we're happy to observe, there was this one false alarm that went out that was some snow plowing person, and we observed 50 galaxies, and fine, we're fine with that. We're happy to do that for one gem that we get very early. So we are happy for LIGO to release something quick and dirty at the beginning, and we start observing, and if they modify it, our algorithm can then modify the galaxy list automatically as it goes.
Can I just comment that there are some people in the LIGO collaboration working on getting triggers before the CBC event is completed, so that you could actually predict, maybe 10 seconds in advance. That won't happen very soon, but down the line that may be possible.
Yes, that sounds really great. I heard about it. Yeah, I guess I'll save us 10 seconds or something, but yeah, I think it's a great idea. I like to hear the LIGO people talking in these timescales now, I think.
So I have rudimentary knowledge of the subject, and I just want to ask two questions. So the first one is, can the in one of the slides there you showed a rise in the data points. Can it be an anomaly?
Okay, yeah, that's a great question. That's actually what people were saying. When we first claimed this rise, we were the only ones to see it in the first few hours. So actually, we began doubting ourselves. But then when I combined the data, so this is, different groups in Chile and different groups in Australia and a different filter, different telescopes, different analysis, and there's a rise here as well, and there is a rise here as well, and there is a flattening here. And so I think that once you see it independently in the different bands, and you see it from different data sets, I think it's real.
Okay. For the second question, is it possible that more observatories like in other countries would give you more data sets, more points, and then it will make it easier for you to find a more perfect model?
Yeah, for sure. I mean, the timescales at the beginning are really quick, so they are less than a day. So you definitely need, the more sites you have around the world, the better. Also, we don't know if the next one is going to be in the north or in the south. So, anyone that can add this with a telescope is great. And here it kind of gets into the balance of, should we be coordinating with other observatories so we're not all searching the same galaxies? Or on the one hand, it's nice that 6 different groups using different strategies were looking at the same galaxy within 40 minutes of each other. Helps us know that this was probably the right candidate. Also, I forgot to mention, we were, because we were using 9 different telescopes in the southern hemisphere simultaneously, we were able to get this data on the kilonova, but also continue observing all of the other galaxies on our list. So we ended up observing about 85% of the mass in the Iair region. So we can not only say that this was an event in there, that there was nothing else also in there as well. So this is also useful for having multiple telescopes, because at the beginning, actually, it was so bright, we were all skeptical that this was the counterpart. So we kept searching other galaxies. And because we have these multiple telescopes, we can do it simultaneously. So we can say not only that this was a counterpart, but that there was no other candidate for a counterpart as well. So definitely the more telescopes there are searching, and if these searches are coordinated or independent, either way, I think the more observatories involved, the better the data we will get, for sure.
Okay, thanks.
If no other questions, let's thank the speaker.
Thank you.